We've done quite a lot of work to this point. We've identified the nodes in a circuit. We've written Kirchhoff's current law at every unknown node voltage. We've converted those KCL equations using Ohm's law, and then we've grouped similar terms to be able to write them as matrix equations. Then we solved those matrix equations to find what the node voltages were. So at this point, we've identified the node voltages. We have V1, we have V2, we have V3 in this particular example, and you would feel like we've done enough work, that we should be able to relax and be done with our work for now. But very often, the professor or your boss will have asked for a different variable. And so here you can see an example of Vx. Here's Vz, we've got I23, we've got I31. These are all quantities that we might be asked to find. And if we were to just return the node voltages, well, then the boss or the professor would say, nope, that's not what I asked for, so you're going to lose points, or you're going to lose credibility with the organization. And that's a shame, because 90% of the work is already done. This last step is actually quite easy. So by comparison, all we have to do is look at here. Let's take Vx, for example. Vx has the positive terminal toward V1, it has the negative terminal toward V2. And as a result, Vx is just V1 minus V2. So V1 minus V2, 14.524 minus 11.429 equals 3.095. So about 3.1 volts is going to be the voltage V sub x. If you were to use a voltmeter and measure the voltages between those two terminals, you'd find about 3.1 volts. Now over here you can see that we have V sub z. V sub z is going to be across this current source, but we don't need to worry about what it's across. We just need to worry about where are the two ends. The positive terminal is up here, and that's toward V1. The negative terminal is down here. That's actually toward V0, which is very nice. So Vz is V1 minus V0. V1 minus V0 is just V1 minus 0, because V0 is the reference node of 0 volts. So it's 14.524. Now calculating current involves a little bit more work, but it's still not too bad. Let's look at I sub 1,3. Well, I sub 1,3 is coming from node V1, and it's going toward node V3. And by the passive sign convention, that must mean that node V1 is at the higher voltage. Now, it turns out that that's correct in this case. 14.5 is higher than 10.7. But if that weren't the case, if it just happened to be that that didn't work out, it just means that I sub 1,3 is going to be negative, which is an indication of the fact that this arrow would be drawn in the wrong direction. In this example, though, the arrow is drawn in the right direction, so I sub 1,3 will be positive. 14.524 minus 10.715, that's the voltage that's going to appear across that resistor. If we divide that voltage by 2 ohms, voltage divided by resistance gives us current. So all we need to do is take the voltage from the source, subtract the voltage at the destination, divide by the resistance, and that's going to give us the current. V1 minus V3 divided by 2 ohms gives 1.904 amps. Similarly, we can calculate I sub 2,3. It's going to be V2 minus V3 divided by 3 ohms. 11.429 minus 10.715 divided by 3 gives 0.238 amps. So once you've calculated the node voltages, any other voltage in the circuit, any voltage difference in the circuit, or any current in the circuit is pretty easy to calculate. And as a result, then we can provide whatever quantities it is that we're asked to calculate, either by our boss or by our professor.